Good morning, students. Today we are going to start with probability of errors. Basically, there are different types of errors: systematic errors, random errors, Gaussian errors. These are the types of errors available in the measurement of instruments. As far as probability of errors are concerned, these errors occur at certain equations. Normal distribution of errors is centrally as given in figure 1.1. You will find that centrally at 100 volt voltage, which we are here measuring the signal, 100 volt voltage signal we are measuring, and the probability of errors within 99.7 volt to 100.3 volt occurs in the measurement. Suppose we are taking total 50 readings of 100 volt voltage. It is distributed as given in the histogram. This figure 1.1 shows histogram showing the frequency of occurrence of 50 voltage readings. Of table 1.1, the broken curve represent limiting case of the histogram when a large number of readings at small increments are taken. That means we are taking total 50 readings. The broken line shows the probability and dark line shows actual observations. On the x-axis we are considering number of observed readings, and on the y-axis we are taking voltage. As given in table also, you will find that there are voltage readings as follows. If we are trying to measure 100 volt voltage, there are 19 times we are getting 100 volt across the instrument. 99.9 volt voltage reading I am getting at around 12 times. 100.1 volt voltage I am getting around 10 times, and 99.8 volt voltage I am getting 4 times. 99.7 I am getting 1 time only, and 103 I am getting once. So there are total 50 readings, and I am measuring 100 volt voltage. Let us see how the probability of these errors are when we plot a Gaussian graph or histogram. This type of error is also called Gaussian type of probability. Gaussian has invented that the probability of error will be of bell shape. It will be a bell shape probability. Number of observed readings are 19 as given in the table of 100. That means accuracy is 20 times accurate reading comes out of 50, means 40% probability of 100% accuracy. 12 times with 99.9 volt voltage or 100.1 volt, plus or minus 0.1 volt voltage occurs majority times, that is 12 or 10 times. Plus or minus 0.2 volt deviation occurs around 4 times or 3 times. So probability of higher error has reduced, and plus or minus 0.3 volt voltage has occurred once. So number of observed readings are 19, 12, 4 and 1 on minus plus side, and 19, 10, 3 and 1 on another side. This is the probability of errors. Normal distribution of errors. There will be a question in the question paper that explain probability of error. What is normal distribution of error? What is Gaussian probability distribution errors? Under this you have to draw this figure and observations under this. Let us switch to the what we observed for that under that observation. Under that observation we observed that we observed that 100-volt voltage readings are majority times. That means there will be a majority of errors of 100. Actually error with nil error is 40% time. Then plus or minus is around 20% time. That means within 0.1 volt plus or minus voltage errors are maximal times. So all observation includes small disturbing effects called random effects. One first thing, there will be always a random errors occurs in the curve or in the reading. Second thing, random errors can be positive or negative. As I told you, there is a reading of 99.9 volt also and 100.1 volt also. So random errors can be positive or negative. And thirdly, there can be equal probability of positive and negative random errors. It is bell shape, means from the central 100-volt voltage it is same or duplicate at negative side and positive sides. So probability is equal across positive and negative random errors. The possibility as to form the error distribution curve can be started as follows. Small errors are more probable than large errors. In the figure you will find that large errors are less. That means plus or minus 0.3 volt error is very less. Hardly one time has occurred when reading was 99.7 or 100.3. Secondly, large errors are improbable. That means 0.3 volt plus or minus readings are less probable in the figure. There is an equal probability of plus and minus errors, so that the probability of given errors will be symmetrical about the zero value. Now we will switch to probable errors. The area under the Gaussian curve between plus infinity and minus infinity represents the entire number of observations. So under this curve between plus and minus sigma limits represent the cases that differ from the mean by no more than the standard deviation. I told you that plus or minus 0.1, plus or minus 0.2 in the above figure are called plus deviation sigma and minus deviation sigma limits. Integration of the area under this curve within plus or minus sigma limits gives the total number of cases within these limits. For normally depressed data following Gaussian distribution, approximately 68% of all cases lie between the limits of plus sigma and minus sigma. That means 2/3 out of 50, 19 are accurate, while 20% are within plus or minus sigma. That means around two-third error signals lies within plus or minus sigma or within very close to 100 volt voltage. Observation has found that two-third comes within the close range of actual reading. For example, I will see a large number of nominal 100 ohm resistor is measured and mean value is found 100 ohm with standard deviation of 0.20 ohm. We generally see under a register reading 10% or 20% accuracy is written. This 20% accuracy comes from the standard deviation. So 0.20 is a standard deviation. We know that on an average 68% all the registers have values which lies between plus or minus 0.20 ohm of the mean value, means plus or minus 2 sigma. As I given you the same example of voltage 100 volt voltage I have taken for 100 ohm resistors. Keep in mind. Probable error here is R is equal to 0.67. That means two-thirds of sigma is the probable error R, plus or minus two-thirds readings comes with this error, probability error. Let us see example. If I consider the resistor of 100 ohm, then deviation factor sigma will be 0.6745. Fraction of total area include 0.5 ohm. Under 1 ohm resistance, that means 1 ohm, you just see over here ohm resistance is this limit. Here you will find under this area there will be two-thirds, that is 0.67 times of maximum total number of deviations. So within this limit maximum number of deviation occurs. That's the meaning of that sigma. We are binding it in the equation. Deviation sigma is 0.6745 of original. 1 deviation, 2 deviation and 3 deviation as given above in this. The same deviation we can say it is here. This will be 1 deviation, 2 deviation, 3 deviation like this. And maximum lies within 0.67 deviation. That means within this jurisdiction maximum probability of readings are there. So this is example where probable error occurs. Okay, probable error is within this region. It is over here plus 1 sigma, then within this range there are maximum readings I want to mention over here. Okay, I am considering example of the instruments. 10 measuring resistance are given below. 10 resistances of value 101 point. Another example I am considering 101.2, 101.7, 101.3, 101, 101.5, 101.3, 101.2, 101.4, 101.3, 1.1 and so on. Find out the arithmetic mean, standard deviation of reading and the probable error. These are the readings, total readings. If I want to find out arithmetic mean, I have to add all these reading, that comes under 1013.0 divided by 10 is equal to 101.3. So average reading arithmetic mean will be 101.3 out of all these readings. Now what I have to do, I have to find out deviation from 101.3. Deviation from this value. 101.3 is arithmetic mean, and for 101.2 deviation is minus 0.1. For 101.7 deviation is 0.4. For 101.3 deviation is 0. For this it is minus 0.3. If I square this deviation, it will be like this. 0.01, 16, 0.16 and so on. 0.36 is summation of this. And 1.4 is summation of this. Now standard deviation equation is given by square root d square upon n minus 1, which is equal to 0.36 square root 0.36 upon 9, which is equal to 0.2 ohm. So standard deviation is 0.2 ohm and probable error will be within the range of 0.6745 sigma, that is 0.1349. So probable error will be within 0.1349 ohm. Means majority out of these 10 readings should lie within 101.3 plus or minus 0.13. That's why it becomes 101.2, 101.3. Second reading I am getting 101.4. 2 again, that is third reading. 101.4 is fourth reading, and again 10. That means there are 5 readings which are lies within 101.2 to 101.4, means 50% probability lies within this region. That means 0.5 is readings which are available within this region. So this is the fraction of total area included. So 50% deviation occurs within this region. That is the meaning of probable error. Now second we will study, that is limiting errors. In most indicating instrument, the accuracy is guaranteed to a certain percentage of full scale reading. I will give you an example of a 0 to 150 volt voltmeter has a guaranteed accuracy of 1% full scale reading. The voltage measured by this instrument is say 85 volt. Calculate limiting error in percent. If I want to read 150 volt full scale, then there will be a 0.1% full scale reading error. Our accuracy is guaranteed 1% to full scale reading. That means magnitude of the limiting error is 0.01 into 150, that is 1.5 volt. If I want to read full scale, then it will be 150 volt with plus or minus 1.5 volt deflection in the accuracy. That is what a limiting error is. 1.5 is limiting error here I want to mention, because accuracy is 1% and for the full scale of 150 volt it comes 1.5 volt. The percentage error at a meter indication is 1.5 divided by 85. If I want to read 85 volt, percentage error will be 1.81%. That is 1.5 divided by 85 into 100%, that is 1.81%. If I want to read for more values, then percentage of error increases. Let us see. If I want to read a 60 volt voltage, it becomes 1.5 upon 60 into 100, that is 2.5% error occurs. Accuracy reduces. if the meter reads 30 volt voltage for the lower voltage, limiting error is 1.5 upon 30 into 100, which is equal to 5% error occurs. The increase in percentage limiting error as smaller voltages are measured occurs because magnitude of the limiting error is fixed quantity based upon full scale reading of the meter. For the full scale it is 1% accuracy. For lower voltage 0.85 volt it is 1.81% accuracy. That means for 60 volt accuracy reduces, that becomes error becomes 2.5%, and for limiting error is increasing to 5% when we read 30 volt voltage. So this is what a limiting error is. Limiting error means 1.5 volt deviation from for full scale deflection, below which our instrument will never read. That is what a probability of error is. Next part we will learn in the next lecture. Thank you.